All right, let's jump right into it. Welcome to today's explainer. We are unpacking something today that honestly feels less like your standard engineering manual and way more like a paradigm-shifting hardware manifesto. We're talking about the K4-PLL architecture. For the focused learners out there who really track the bleeding edge of digital signal processing, you are going to love this. We are looking at a blueprint that fundamentally rewrites the physical limits of hardware by completely escaping what engineers are calling the Cartesian trap. There is this profound concept right at the beginning of the source material that says, if the universe acts as a macro PLL triangulating the discrete grid, we must look at how human engineering currently attempts to replicate this. Just think about that for a second. It frames the universe itself as this massive phase-locked loop, a macro PLL that perfectly triangulates reality. And human technology? Well, our 2026 baseline technology is struggling to mimic that frictionless reality. We're essentially out there fighting against our own math. So to understand how we actually fix this, here is our roadmap for the explainer. First, we diagnose the illness, the Cartesian trap. Second, the cure, the tetrahedral mesh. Third, the enforcer, the quantization gatekeeper. And finally, the real-world result, perfect analog synthesis. Which brings us to the absolutely crucial question we have to answer. How do we escape the Cartesian trap? Because right now, it is a catastrophic mathematical flaw that's crippling our most advanced 5G, 6G, and radar technologies. But to escape it, we first need to fully understand exactly what it's doing to our processors. Section 1. The Cartesian trap, a crisis of computational exhaustion. Seriously, our hardware is literally exhausted from doing heavy, completely unnatural math. So right now, we basically have two legacy approaches. First up is the standard all-digital PLL, or ADPLL. This operates purely on 1D temporal forcing. It essentially just looks at a wave and says, hey, did you arrive early or late? And then it violently snaps the clock to correct it. It's kind of like a microscopic hammer. It completely ignores the geometric shape of the energy, which generates massive localized heat and noise. Now, the other approach is the vectorized square PLL. This tries to be a bit smarter by mapping the signal onto a 2D Cartesian plane, your standard in-phase and quadrature square grid. But it commits a totally fatal error called Cartesian decimation. It projects actual physics onto a rigid 90-degree orthogonal grid, which forces the signal into floating point decimals. Let's unpack exactly why that square grid is so exhausting for our hardware. When you map an angled vector onto a 90-degree grid, its position is almost always going to be somewhere in the empty space between the axes. So, to find it, the processor is forced to constantly run heavy trigonometric functions, sines, cosines, or tangents, just to calculate a simple hypotenuse. You are basically forcing the physics of the wave into floating point decimals, and decimals decimate the vector. The signal slowly bleeds its energy into decimal rounding errors. You end up with massive algorithmic overhead, a ton of thermal heat, and inevitable phase noise. We are literally burning processing power trying to calculate empty space. And that brings us to the breakthrough, Section 2, the tetrahedral mesh, rewriting the rules of physics. So how do we build this new reality? Well, we completely throw out the 90-degree Euclidean axes. The K4-PLL architecture fundamentally rewrites these limits to achieve perfect fidelity by replacing continuous math with a 3D triangulated integer mesh. Suddenly, there are no empty spaces anymore. It's a continuous scaffold made of perfectly rigid equilateral triangles. And because it's triangulated, we don't have to calculate angles across empty space at all. We just hand the signal off along a pre-existing integer edge. We instantly swap out all that heavy trigonometry for frictionless boolean combinatorics. But you're probably wondering, how do we get legacy algorithms to actually work on this radically new mesh? We use an intercept wrapper that follows 3 exact steps. Step 1, the coordinate translation layer intercepts those old XYZ floating point decimals and instantly converts them into a 4-part baryocentric discrete vector. Step 2, the quantization gatekeeper violently snaps any leftover fractions to the nearest integer. And step 3, we completely redefine the distance metric. We stop using the Pythagorean theorem to measure Euclidean space, and instead we use topological Hamming distance. The algorithm just efficiently counts the number of Boolean edges between nodes. No more square roots bogging down the entire system. Moving on to Section 3, the quantization gatekeeper, eradicating phase noise. This right here is the absolute core of our explainer. Meet the K-basin operator. Now, traditional PLLs rely on integration filters that slowly ramp up a variable to catch up to a phase lag, which unfortunately generates noise. The K-basin logic block replaces that entirely.
It actively monitors the vector, and if thermal noise or external interference attempts to push the signal into an invalid decimal state, the operator instantly applies a geometric parity check. It forces the vector to snap to the nearest mathematically permitted integer node on its 192-state local graph. And because this relies on spatial proximity rather than temporal integration, this correction occurs in a single clock cycle, zero lag.
Now, to physically build this into an FPGA chip, we have to perform some major architectural surgery. We completely rip out the standard arithmetic logic unit, the ALU that relies on floating point math, and we replace it with a pure combinatorial logic core. We're talking logic gates routing the data, and/or XOR, all feeding into a multiplexer. The processor no longer calculates angles, it strictly calculates routes using a boolean adjacency matrix. Moving a vector 90 degrees out of phase doesn't require a square root anymore. It literally just means shifting the ones and zeros a few edges down the triangulated mesh. I absolutely love this analogy from the source material. Think of standard floating point technology like driving a car on an open, featureless salt flat. You are constantly drifting and having to make microcorrections just to stay on your angle. The K4-PLL, however, rides on rigid Boolean train tracks. Because the signal is structurally forced to travel along these rigid Boolean edges, fractional drift isn't just corrected, it is structurally impossible. The tracks simply do not exist anywhere except on the integers. Section 4. Perfect Analog Synthesis, the Pristine Illusion. Let's look at the real-world results. Okay, so what happens when the K4-PLL needs to translate its digital processing back into a macroscopic analog waveform, like an audio envelope or a radio transmission? Through its K4 to DAC output layer, it uses pure integer-based interpolation. Think about what this actually means. The internal signal suffered exactly 0 rounding errors and 0 phase jitter during its processing. Because of that, the resulting analog envelope is mathematically pristine. The architecture flawlessly renders this continuous illusion out in the real world, specifically because its underlying discrete integer reality was never, ever compromised by floating point fractions. Let's run through the system terminal ledger for the K4 DSP Gold Master. This is basically the checklist of a hardware revolution. ALU status? Removed, replaced by a combinatorial lookup table. Floating point? Eradicated across all registers. Phase math? Now handled purely by Boolean adjacency matrix multiplication. And clock efficiency? Optimized to single-cycle error correction via the K_basin snap. The Cartesian trap has literally been engineered out of existence. To put all this into perspective and highlight why this matters so much to us, we are talking about the total structural eradication of phase noise. The hardware itself forbids it. The signal strictly travels along rigid Boolean edges. The geometric parity check instantly snaps any topological deficit into its proper discrete integer place. When you have total elimination of decimal jitter, you can maintain perfect phase coherence over effectively infinite bandwidths. And that leaves us with this massive, undeniable takeaway. Phase slip becomes mathematically impossible. We aren't just filtering noise better anymore. We are using 3D integer geometry to ensure the noise cannot mathematically exist in the first place. So I'm going to leave you with a final thought here. If we can completely eradicate noise in digital signal processing simply by ditching the square and embracing the universe's native discrete geometry, what other flawed Cartesian systems in our world are just waiting to be violently snapped into a perfect triangulated reality? Where else is our math blindly fighting against physics? Keep that in mind as you look at the systems all around you today. Thanks for joining me on this explainer, and keep learning.